Buffers consist of a weak acid, which we will represent as HA, and its conjugate base, which is represented by A-. And buffers resist large changes in pH. Buffer capacity refers to the amount of acid or base the buffer can neutralize before the pH starts to change by a large amount. To better understand buffer capacity, let's start with a buffer that has an equal concentration of the weak acid HA and the conjugate base A-. Looking at the Henderson-Hasselbalch equation, the pH of the buffer solution is equal to the pKa of the weak acid, which is HA, plus the log of the concentration of the conjugate base, A-, divided by the concentration of the weak acid HA. So if the concentration of the weak acid is equal to the concentration of the conjugate base, the ratio of their concentrations is equal to 1. And if the ratio is equal to 1, the log of 1 is equal to 0. Therefore, the pH of the buffer solution is equal to the pKa of the weak acid. So we're going to start with our buffer solution having a pH equal to the pKa of the weak acid, and we're going to think about what happens to the capacity of that buffer to neutralize added acid or added base. It's also important to note that this ratio of the concentration of conjugate base to the concentration of weak acid, that ratio is what determines the pH of the buffer solution. So as the ratio changes, so does the pH. So we're starting with our concentrations equal, and the pH of the solution is equal to the pKa of the weak acid, and our ratio is equal to 1. Let's think about what happens if we add some acid, some H+, to our buffer system. The acid that was added gets neutralized by the base that's present, which is A-, to form HA. And because we're using up the A- to neutralize the H+, the numerator of our ratio would get smaller. And because we're forming more HA, the denominator would get larger. So we started out with our ratio being equal to 1, but after we add small amounts of acid, the ratio will be less than 1. And as we add more and more acid, the ratio will keep getting smaller. As long as the ratio stays relatively close to 1, the buffer is able to resist large changes in pH. However, when this ratio goes below 1/10, the buffer is usually no longer effective at resisting changes to the pH. Therefore, if we were to add small amounts of acid at this point, the solution is no longer buffered effectively and the pH would change dramatically. Let's go back to our buffer solution when the concentrations of weak acid and conjugate base are equal to each other, and the pH is equal to the pKa of the weak acid, and our ratio is equal to 1. However, this time, instead of adding acid, we're going to add some hydroxide anions. We're going to add some base. The base that's added is neutralized by the acid that's present, which is HA, which forms water, H2O, and A-. Because HA gets used up when it neutralizes the base, this time the denominator decreases, and since we're forming A-, this time the numerator increases for our ratio. So we started off with our ratio equal to 1, and as we add small amounts of hydroxide anions, this ratio gets larger, therefore it would be greater than 1. As long as our ratio stays relatively close to 1, the buffer solution is effective at resisting large changes in pH. However, as we add more and more hydroxide anions, the ratio keeps increasing, and when the ratio is greater than 10, the buffer solution is usually no longer effective at resisting large changes in pH. Therefore, once we pass this point, if we try to adding some more hydroxide anions, the pH of the solution would change dramatically because the buffer system is no longer effective. So we've seen that the effectiveness of a buffer depends on the ratio of the concentration of the conjugate base to the concentration of the weak acid. Let's use that concept to compare two buffer solutions, so buffer solution 1 and buffer solution 2, to determine which of the two has the higher buffer capacity. Let's say that both buffer solutions have the same weak acid and conjugate base present, however, they differ in terms of their concentrations. So solution 1 is more concentrated than solution 2. Because both solutions have equal concentrations of weak acid and conjugate base, both solutions would start with the pH being equal to the pKa value. Let's first think about buffer solution number 2, which has the lower concentration of weak acid and conjugate base. Because the concentrations are lower, if we were to add either acid or base, the ratio would change faster than in the other solution. Therefore, solution 2 has a decreased capacity to neutralize either added acid or added base. Therefore, we say that solution 2 has a decreased buffer capacity. Buffer solution number 1 has a higher concentration of weak acid and conjugate base compared to buffer solution number 2. Therefore, if we were to add either acid or base, this ratio would change slower than in solution number 2. And so solution number 1 has a better capacity to neutralize either added acid or added base. So we say that solution 1 has a higher buffer capacity. Another way to think about buffer capacity is to imagine we had these two solutions, solution 1 and solution 2, and both started out at the same pH. And then we added either small amounts of acid or small amounts of base to both buffer solutions. At first, in both solutions, the pH would remain relatively close to the pKa value because buffers resist large changes in pH. However, since solution 2 has a lower buffer capacity, eventually the buffer would stop being effective and the pH would change dramatically. Because buffer solution number 1 has a higher buffer capacity, we could add more either acid or base to it before the buffer loses its effectiveness. Buffer solutions don't have to start with an equal concentration of weak acid and conjugate base. For example, when the concentration of weak acid is greater than the concentration of conjugate base, the buffer has a higher capacity for added base than added acid. And when the concentration of conjugate base is greater than the concentration of weak acid, the buffer has a higher capacity for added acid than added base. As an example, let's think about blood, which has a pH of 7.4. The major buffer system used to control the pH of blood is the carbonic acid bicarbonate buffer system. In blood, the concentration of bicarbonate is greater than the concentration of carbonic acid. And since bicarbonate is the conjugate base to carbonic acid, the concentration of the conjugate base is greater than the concentration of the weak acid, and therefore the buffer system has a higher capacity for added acid than added base. The reason why the buffer system needs to have a higher capacity for added acid is because the products of metabolism that enter the bloodstream are mostly acidic, and therefore the bicarbonate anion can react with those acidic products and neutralize them. Therefore, the buffer system is able to resist large changes to the pH of blood.